So quick sidetrack about applicatives. If I go to another screen. So if I do stack GHCI here, let's say I wanted to do some sort of validation. What you could use is either as a monad, right? So things, either string, let's say int. You could say does this make sense for now?
With right and left is the data constructors deriving.
Yep, exactly. This should compile. Right. Now, if I do validate two things, I will get right 4, right? But now, let's say one of them violates, and I say -1, for example, then I get a left. It's saying not greater than 0. But if both of them violate, I still only get one error, namely the first one. And so if this was a different kind of either applicative, where the errors are accumulated, then I could maybe see both of them. So let's say I do the validation applicative, where this is error with a list of errors, or okay with only an A, right? Can you convince yourself that this is somewhat similar to either? So now if I say for any E, this is a functor, and I fmap my function over error with the list, it's just the error again. This is just typically what you expect. This still makes sense? Now, if I write my applicative instance, pure is just OK, and then v1, v2, case v1, v2 of. So if I just get OK twice, then I apply the function to the value. That makes sense. But if I get an error in either case, then I want to return the errors instead. Still with me so far?
Yep. Do you want instance applicative on the second one?
Yep. Right. And now, if I have errors in both cases, then I want to add those two together. Now, if you implement the monad instance for this, and you can implement a monad instance for this, it will not be law-abiding. Because in the case of monad, you cannot combine the two errors if there are both errors, because you have to completely run the first function in the bind before you can start with the second one. So you can only start with the second one if it wasn't an error. So you can never combine both of the two errors in the case of a monad. This is a motivating example of why sometimes you want something not to be a monad. And the way you do that then is by doing this, for example. Oops. Like so. And now I do validate two things. Oh, right, I need... Voila, and now I get both the errors. But you cannot write a monad instance for this applicative. Well, you can, but it won't be law-abiding. And I'll show you if you want. This is the monad instance that you could write, but this is not law-abiding because it doesn't do the same thing as applicative when you use the applicative style application. So this is not a valid monad. And in fact, if I rewrite this to be different, like you would expect to be equal, then you get a different result, which shows you why it's not law-abiding. If I do this instead, then I get only one of the errors. Does that make sense?
Got the value back from validate GT is 0.
So let me desugar this for you. Yeah, so that's a valid desugaring. In order for this A to exist to put into validate GT1, GT0 must already have succeeded. So you cannot combine the two errors. Because this thing is never run if the first one fails already. So the power of the applicative is that you can reason about the entire tree of things that happen without having to get the result of one thing to go into the other. But that is also a problem if that's exactly what you want to do. If, for example, you want to make valid GT1 depend on the result of valid GT2, then, so 0, I mean, then you can't do that in an applicative kind of way. Because there's just no way to produce the output already before you go into the next thing. So what I can't do is this, for example. Well, I can do it now because I have a monad instance, but if I remove the monad instance, then this thing doesn't exist anymore, and then it's not possible.
Is it an incorrect interpretation to say that like a monad is going to sort of dependently sequence computation?
Yeah, that's exactly right.
Okay, and then applicatives are like independently, these are going to happen in this order regardless.
Yeah, that's exactly right. So monad encode data dependencies. Monads encode data dependencies. That's exactly why they were invented for I/O as well, right. Because that's the entire point, right?
Yep.
All right. What time is it? All right. So this next talk is about an overview of all the different kinds of way of doing property testing. Are we all here? Oh, hi, Ryan. So if you like what I'm going to tell you now, I wrote a big long blog post about everything from scratch for property testing all the way to this overview that I'm giving you now. It's on the FP Complete website, and I'm sure you can find it. So that's the material that I'm going to be showing you, minus the how to do property testing, because we've already done that. So there are a whole bunch of kinds of ways of doing any property testing related things in Haskell. It started with quick check, and now there are a bunch more. So the important ones are Hedgehog, which is a relatively recent, which has a bunch of other different trade-offs. And then there's Validity, which has different trade-offs entirely as well. Then the things I'm not going to talk about are Speculate, Lean Spec, small spec, exhaustive spec, and not yet quick spec, easy spec, and a bunch of other things. So small check is for exhaustive testing. If you want to run a function for all of the possible inputs instead of just random ones, that's what you use small check for. And the other ones are, they're all related to research efforts, but I want to show you the real practical application of this thing instead of the theory. So you need three things for property testing. I've already explained this part. You need the property to test, you need some generators to generate the input, and you need some shrinking mechanism. I'm talking about randomized property testing here, so not the exhaustive ones. In quick check, the ways this happens is that you have this type check called this class called arbitrary, which has a function called arbitrary, which is a generator for the thing that you're describing the instance for. And it also has a method called shrink, which, sorry, not a method, a function called shrink, which allows you to define how shrinking works. So that's the shrinking function for the A, not for the A. The important thing to realize here is that shrink has a default implementation, which is don't do anything, don't do any shrinking, and arbitrary has no default implementation. So by default, you have to write every generator yourself. You can compose them, but you have to write it yourself. And by default, there is no shrinking happening. So if you want shrinking, you have to do it yourself. And this is how you write a property in quick check. So you say quick check, use the argument string, for example. Use the argument str, which is a string. Reverse it twice, should be the same as the original. And then quick check will run 100 tests. That's what it looks like in quick check. Now, the reason I show you this is because it looks very different in the other frameworks. So I've already explained some property combinators, but I have to reiterate it a bit. So let's say we have this binary relationship that I call the floopsy, because I don't want to pronounce these characters. Now, if I want a property combinator to check if this is reflexive, I can abstract out of that, make a function that takes an argument that is the operator, and then make the property that tests the reflexivity. We've already seen this part. Now, why do I reiterate it? It's because of the person who was sitting there. They had a really good question that I'm now going to answer, but he's not here anymore. This requires the arbitrary instance for the arguments. So you have to either give an arbitrary instance constraint or pass in a generator to do the generating with. Now, it's important to realize that that means you cannot use these without, you cannot use this if the property that you're trying to test doesn't hold for all of the things that are generated by arbitrary. So for example, if you try to test for reflexivity of, it's a bad example, if you try to test for things involving rational numbers, then usually what you mean is normalized rational numbers, where, for example, 2 divided by 2 is supposed to be equal to 1 divided by 1, but in Haskell, in rational, that's not the case, because usually you can't construct these things very easily. So usually you want your code to work for all the normalized rational numbers, the one you expect, and you don't need to necessarily have it hold for these strange cases, like 2 divided by 2 as a rational number. So the problem with arbitrary is that there are no laws and no semantics for it. You can write any generator you want. You can write any shrinking function you want. You can shoot yourself in the foot really easily. So the problem is, what kind of values do you expect to have generated here? For generating rational numbers, so that's just one thing divided by something else, represented as 2 numbers. Would you want to generate 0 divided by 0, which is not a number? Or would you want to generate 1 divided by 0, which is just plus infinity, I think? And or if you have ready answers for these, like yes, definitely, or no, definitely not, maybe do you want to generate 5 divided by minus 0? Maybe not, but if you think, what did I do again? If you're fine with generating 5 divided by minus 0, maybe you're less fine with minus 5 divided by 1. And like, you have to start thinking about these things now, because it's important for your arbitrary type class, and you have to make this decision. So if you never generate unnormalized values, then you never test these edge cases. If you only generate, if you do generate unnormalized values, then equality breaks, for example. So in every situation that you choose here, you will have a problem. And the way quick check deals with this is to have new type wrappers around the values to have different kinds of generation. So in the case of rational, you may have the normal arbitrary instance generate also unnormalized values, and then you may have a normalized wrapper for which you can write a separate instance, arbitrary of normalized rationals, that only generates the normalized values. The problem then is now your property combinators break because you have to specify this new type wrapper every time where you're going to want to use this different kind of generator. So once you use these new type wrappers, the property combinators don't compose anymore, because now, let's say your thing is reflexive, but reflexive, yes, for unnormalized values, but not, let's say, associative. I'm just making something up. Oh, that doesn't even work, does it? So reflexive, but not transitive, for example. Then you want a different generator for each of these, and you can't put them together in property test suite combinators anymore, because for one thing you want the new type, and for something else you don't. So this kind of breaks apart in real scenarios very quickly. The other problems are that there is no default implementation of arbitrary, so you have to write all of them yourself. And in fact, there is a comment about this in the code saying that we don't have a default generator because we don't know how to write a good one. And I argue that any one is better than none at all, because now you still have to write it yourself. And actually, you could write a relatively good one that is potentially more expensive. And by default, there is no shrinking, which means that if you want shrinking, you have to write it. We analyzed Hackage. About 1 in 6 arbitrary instances actually has a shrinking function defined, and some of them are wrong. So people don't seem to do it. And I know that Hedgehog was invented for this entire reason. So I'll get to that in a moment. First, the next question is, where do you put these arbitrary instances? If you put them in your code, then your code needs to depend on quick check, which is not something you want for your production code. If you put them in your test suite, then you have to repeat the arbitrary instances for your own code in every different test suite, and you can't import a test suite, so that means you have to copy paste them all over the place. And then what usually happens in quick check is that all of the instances are put into one package on Hackage called quick check instances. But if you import that, then you're depending on a whole bunch of things that you never asked for. And they're now a dependency, and you need to compile it for your project. You can also put them in a separate library, but then you have orphan instances, maintenance overhead, all sorts of nonsense. So there is really no good way to deal with this. What we've kind of settled on is the extra library and just take the maintenance hit, because then at least you can do the other things that you should be doing. Right, so Hedgehog started to exist to solve most of the problems with quick check. This is how you write a generator in Hedgehog. And you'll notice that this is way more complicated already. So you have to import 3 things. Hedgehog is where property comes from. You have to import the generators, which is how you specify your generators, and then range to specify how the generators should behave. And then you say, for any list of characters which have a size that is linear from 0 to 100 and also shrunk that way, make this property testing function that if you reverse something twice, it's the same as the original list. This is way more complex, and you have to specify your own generator every time. So I'll get to that. Hedgehog does not have a type class at all. It has value level generators only. It has built-in shrinking into the generators. And the way that works is with a, what was it? I think it's a trees transformer over a maybe. It's a tree of, it's complex. So the idea is that instead of generating some values and then shrinking them back, the generation and the shrinking happens at the same time using a lazy tree of possible shrunk values. You don't need to understand how that works. It's built in, that's the idea. And it also allows you to have more general generators that can also do monadic effects in the meantime. It's arguable whether that's a good thing. So the way the shrinking works in Hedgehog is such that if you compose your generators, it automatically composes the shrinking functions for you, which is really nice because then you don't have this problem that no one writes their shrinking functions, and it's also not wrong because they're automatically correct. But in Hedgehog you have suboptimal shrinking in the sense that it will generate the same shrunk value many times, and this is potentially a performance problem. Or I haven't seen it. Yeah, I have seen one correctness problem with it. So what you see here is if you generate either an A or a B, so that's what this says, put them together in a tuple, and then filter out the tuples where the first and the second character are the same, and then show me the shrinking tree. It says this is the generation, this is the thing that was generated, these are all the possible shrink. And you notice that the same shrink occurs many times. And there is only 3 of them right here because it's A and B, but if it was A and Z, this could be like 26 levels deep, and you'd have exponentially many more of the same shrunk values. Now, this is not necessarily a problem in practice because this tree is lazy. The way QuickCheck deals with this is also wrong because it just gives you an empty list instead of shrinking to AA. And just a quick little foreshadowing, validity-based testing does this correctly and just gives you only the value, only the list of one value, which is A and A. Everyone still with me? Any weird questions? Any questions until now? Anything I said that was weird? No? Okay. So this is one of the problems with Hedgehog. The much more bigger problem is that you have to write every generator yourself. There are no instances. There is no type. There is no instance. There are no instances because there is no type class. What did I do now? Keep doing this. Right, so if you want to write your property combinators, you can't rely on a type class. You have to pass in a generator. And this is really tedious, especially because if you write your combinators, you may want to use different generators for different pieces of your combinators. Do you have a question? Or? Okay. So you need to string the generators around if you want to pass them in somewhere. So that's another problem. And this overhead of having to write generators is often big enough for people just to not bother at all. So my work has been about how do we make testing cheaper and easier instead of more sound, for example. So validity-based testing is supposed to be a solution to the problems of the previous two. The ideas are to get free generators, free shrinking, and very cheap properties. And the entire next hour tomorrow night will be about validity-based testing. But first I want to show you some examples of the QuickCheck and the Hedgehog thing. I went through this a lot quicker than I was supposed to, so I have some time to show you some examples. So let's say I import Hedgehog and also QuickCheck. I opened this somewhere else already, didn't I? Okay, so now I can import QuickCheck. You've already seen how that works. Let's say we have some of our own data type, and I recommend you join in, so I'm going to commit what I made here in a moment. So I'm going to come up with a little data type and ask you all to write shrinking functions and also generators for them. So let's come up with a silly little data type. Let's start with the sum type. Int or string, where it can either be an int or it can be a string. The next thing I want to come up with is, let's say, my type, which is a record. I'm going to push this in a moment so you don't have to copy paste what I'm doing. And then we're going to write some generators for that. And the last thing I want to do is also some sort of tree, let's say a ternary tree. Like so. There we go. You should be able to pull that now. Sure. Hedgehog.gen, yeah, that was it, right? Ah, it's without the second H. Okay, so the idea here is to write instance. I'll commit this again because I made a mistake. Right, if you pull again, then these imports should be fixed. So now let's write instance arbitrary int or string. What did I do now? Oh, okay. I suggest you try it. If anything comes up that doesn't work very well, let me know, and then I can walk through it with you. I'm also going to reiterate the types.
Fell off a little, so.
Can you stack GHCI in :R so that you can see what's going on?
No, no, I mean.
Can I spy on you? Me? Oh.
It's trying its best.
Seems downloading QuickCheck and building it took a lot longer than expected. Ah.
So you find that as soon as you take Unix tools on Windows and a lot of context, it's like, oh, that takes approximately 1,000 times longer.
Oh dear. I see a lot of very different tooling as well. Some people use just the command line thing in Windows. Some people have a full-blown IDE. A few people use Vim as well. So I'll remind you, if you have written something that you want to see how whether your generator makes sense or what it does, you can use sample and then arbitrary colon int or string. Gen int or string. And now I need to do q.gen. Voila. So this call is undefined for me because I haven't written anything yet. Does anyone have anything that they want to put here? Any generator already written? Well, I'll wait some more. Stack GHCI.
Colon L space file name.
Right, you shouldn't have to do that though. That should happen automatically. You run. You have to be in the. Yeah, now try stack GHCI. I'll put together some building blocks. So there's the arbitrary building block that you know about. And then there is one of which takes a list of generators and makes a generator that chooses from this list. And then the other one is such that gen A that can filter. Does anyone have any generators already? Oh, you're waiting for quick tick to build, yeah. What are you Googling? Is this
how to write any arbitrary, like even a generator? You had it previously in past slides.
All right, let me write the first half of this generator and then you'll have an example. So if I write arbitrary here to generate an integer, now I can use this first constructor called I as a function that takes an int and produces an int or a string. If you have some function that you want to map over the generator, you use fmap. So fmap in the case of generators is A to B gen A to gen B. So fmap is the same as this thing. So what you can do is you can fmap I over this arbitrary. And now a sample. Here's an example. Is that what you were looking for?
Not really. I was looking for a basic example. So effectively, q.gen is also a constructor.
No, q.gen is just a type.
Oh, okay.
Is it clear what's meant here?
Yeah. But do we need to specify the type explicitly?
No, I was just trying to show it. So you can write it like this as well. All right, so now we have a generator for only 1/2. If you were to actually write tests using this generator, then you will most likely be hiding bugs because the other kind of value is not being generated. So you also need to write another generator for the strings. S fmap over arbitrary for strings, that is. This won't compile because this is a list of generators and not one generator, and then you can use on this list and it will choose one of them. And then you have a sample. Then you have a generator that can generate any value of int or string. Does this make sense? So the next thing to do is to write the shrinking function. So that means we're going to have to decide what it means for one value to be easier for humans than others. So you could say that, for example, ints are easier than strings, but there is no real way to make a smaller kind of int out of a string. So what we can also do is stick with the constructor that we have and generate a default value for the others. So if we say that int is easier than string, then we can make a shrinking function that behaves like that. Now it's really important to notice that you should never, well, you must never make a shrinking function that maps a value to a list that contains itself. That contains that value, I mean, because then you will have an infinite loop while the shrinking process happens, because the shrinking process works recursively. So we can say, if we find a integer, then just shrink it like you want. So this, what I wrote here, is the nice functorial way of writing that. You can also write that in a more readable fashion, like so. It's the same value. So in this case, we say that if you find a counterexample with an I, then to shrink it, you shrink the integer inside and you make another I. And then for strings, you can do the same. But now the problem is, it could be that because we've decided that an integer is easier to reason about for a human than a string, if you have a counterexample with a string, and it would also be a counterexample if it was an integer instead, for example, something that just always crashes, then maybe you want to show an easier example to the human. The problem is there that you can't really create an integer from an S, but what you could do is generate a default value like so. So that what we're saying here, the simpler versions of an S constructor with a string inside is first, the simplest version is just an int that is 0, and the others are whatever happens if you shrink the string inside. So that means if we have a significantly wrong property, we'll still get a very simple output value, for example, I0. Does that still make sense? Is there anyone who thinks I would definitely not have come up with this? All right, so is it something you don't understand, or is it just not, is it just that you don't have the experience with this?
I would guess experience, yeah. I'm getting kind of lost with syntax.
Aha, okay, so is there any specific syntax that you don't understand?
Well, I don't really get why we're mapping the I and the S over this and what they do.
Okay, so let me show you how this works first. If you want to shrink an I of 5, let's say, then it generates a few shrunk values of the I. If you shrink an S of hello, then it will generate a whole bunch of shrunk values of that, and also the I0. Now, we already have a shrinking function for integers and for strings because they are an instance of arbitrary. So we can use that. So you don't have to decide what a simpler integer looks like or a simpler string looks like. But if you would say, write this, then shrink I produces a list of ints, which is of a different type than int or string, which means that for every one of those shrunk ints, you need to put them into an I again in order to have the type correct. Does that make sense?
Are there already shrinks for enumerable characters in the language in general? Because that's going to be like 90% of the scenario.
Yes, there are shrinking functions available for that.
So unless you come up with some very basic core type, you're always going to use the shrinks that are already kind of tool, I guess.
Yes, but it could be that you could come up with some examples where the shrinking function that is already in the library is not going to shrink to easier values for humans.
Okay.
So for example, if you want to shrink a phone number and you save it as a string, for example, then the shrinking function will be wrong because it will shrink to values that are not phone numbers. So even though the shrinking value generates simpler strings, it's definitely not a simpler phone number.
But you would still use this shrinking inside the tooling for shrinking the prefix and stuff like that.
Yeah.
After you split it into bits.
Yeah, and then also make sure that the shrinking function, even for the bits, also only generates strings that are numbers.
So how would you go about shrinking structure?
Yes, we'll get to that. So if you have a recursive data structure, you shrink to the simplest thing first, and then shrink to the subparts of the thing that you have, and also recursively all the shrunk values of those. So there is a nice piece of documentation about that. Oops. Here is the explanation of how to shrink a tree. So there are 3 things you want to do. These are the 3 things you want to do. For tuples, yeah. And it's important to realize that you don't shrink the values individually and then put them together. You really shrink the tuple. If you shrink the values independently, then you may get a very weird, very complex version of one part of the tuple and then an easier version of another before you even get the simplest version of all of them. Does this still make sense? Sorry?
Thanks, I never understood.
Oh.
Certainly repeat that.
So I'll have to give an example. So there are 2 possible ways to do the shrinking for a tuple, right? Let's say I have a tuple A and B, which are 2 integers, and I shrink them like so. You make a tuple out of 2 shrunk versions where the first element is the shrunk version of A, and the second element is the shrunk version of B, but you shrink them independently. Now if I shrink 5, 6, you'll see that the zeros in the first element come way before the zeros in the second element. So you always shrink the first element first, and then and only then will you shrink the second element. So this is here you have all the zeros, there you have all the 3s, and here you have all the 4s, right? Now if you shrink it differently, if this is not different, then my career is a lie. Now you immediately have the shrunk version of both of them in such a way that the this may be a bad example though. I can't seem to find a good example of this. So what you want is the simplest version of both the arguments of the tuple together, as opposed to shrink one of them independently and then shrink the other one independently and build up the list like that. The reason is that what you want to show to the user is the simplest possible version of in both arguments and not just in the first, and if there is any simpler thing to do in the second, then the second. The way, what happens here is that to get, let's say 0, 0 is not the right thing to shrink to, is not something that fails the test, but 3, 3 is. 3, 3 will be a lot later in this list than in another kind of list that you would make when you shrink a tuple. Now, I can't seem to show you a nice example of that, but the idea is, see if I can come up with a better example.
You don't want the shrinking situation.
Yeah, that's right.
Is that if you're shrinking the values independently, then the shrink function will be acting on the values independently, which means that the results will not be combined the way that you expect. But if you shrink the container of the values, then the shrink function will be acting on the values together, essentially at the same time,
Mm-hmm.
in the same way.
Yeah.
And so you're more likely to get the value that you are hoping for.
Yeah. Yes?
Two questions here. I don't remember if the shrink is pure or if it's seeded. Seeded of some sort.
No, it's not seeded. It's pure.
So running the shrink multiple times.
We'll get to the same values.
Same result all
Yeah.
the time. Second, this seems to be an awful lot of effort in making error messages readable.
Yes.
In theory, you write a test or a specification.
Yeah.
And hopefully it stays green. That's kind of the idea. So
Yeah.
I don't know if it's worth putting this effort in instead of looking at the diff on the code at that point.
Yeah. So it depends on your situation, of course, but the way I usually do it is I write, let's say I'm writing a JSON parser and a renderer. I'll write a function that says, for example, if I render my value and then I parse it again, then it's the same as the original value. As long as the test is green, I will not touch the test anymore, because that means my thing works. But now if I have an example, I get some complex example with a smaller shrink version, and then I want to figure out what the real problem is, so I'll write more granular tests, where I say, for example, this thing holds when I use a generator that doesn't use recursive JSON, or only uses numbers, or only uses strings, or whatever. And then I get much more granular error messages by writing more tests, and I can just leave them afterwards if my code works again. And in that case, you want the shrinking to, when this thing becomes red, you want the shrinking to work, because otherwise you'll get, this is not a joke, hundreds of terminal pages full of one value. I had this recently, actually. Was it this one? Well, now I fixed it, so. I may have to run it a bit more. It's gonna take ages. I don't remember where I fixed it. this is doing an API call to an actual server every time, by the way. I mean, I run the server locally, but still.
So effectively you run this kind of in a fuzzy way, and then when you have an example that fails, you transform it into a complete test.
Yeah, so I had this thing that failed, is idempotent, and then I wrote these two. Those are more granular.
Yes.
But I should probably have to. I have such great error messages for my own project. I think this will be a nicer example. So you saw that I wrote more granular tests for a thing that I will hopefully now be able to show you that failed because of the size of the output and what's going on. So what's happening here is that I'm synchronizing some data records between a client and a server in a conflict-free manner. And something was wrong somewhere because I messed up a JSON decoder. And that... what? Oh, I didn't turn off the shrinking yet, did I? Damn it. If only I'd known that I would show you this, then I would have prepared and I'd figured out which commit this was. There we go. Here is an error. And this is not even the worst one. But yeah, so here is an error. Now go figure out what the problem was, right?
So there's like one character somewhere different or something like that?
Yep. So the problem is that I have a list of tuples where the first elements of the tuple needs to be unique. And it's not somewhere in here. And actually, I already have the nice explanation that these UUIDs are not distinct. But go and figure out where, right? So what I did then later was to make the output a bit more legible. But then it's still enormous. This is not it yet. There is this package that I use for my testing output a lot, which is called Pretty Show, which instead of showing this big record on one line, shows you a nice, let's say, clearer version of the record. How much time do I have? Yeah, okay. I'm almost done anyway. Ta-da. So here is your error message. Right? So at least it's not one line, but you still don't know what's going on, right? So the problem here is that these two, sorry, no. Yes, so here the problem is p map is equal to p map of empty list is equal to p list of empty list, and
Still better than object is not equal object.
yeah, absolutely. So now try and figure out what the problem is here. So that's why you write more granular tests afterwards. Now where is the code that I was working on? So we have a few more minutes, so I'll just give you the solutions to these. This will work, I think. Oh, right. So what that means is generate a Boolean, generate a rational, put them together in my type. Voila, and then I get some nice values. Now for the leaf, for the tree.
What about tree?
Right, good point. Shrink my type and now shrink one of these. Ta-da. So there is your shrinking function. What it does here is it puts these two B and R in a tuple, shrinks that, and then the results puts it back into my type. So the other thing is arbitrary. If you want to generate a tree of A's, then the A needs to be generatable. But let's do it without the A's, just for brevity. So this is a ternary tree with no values in it. So what you could do is one of pure leaf, branch, arbitrary, arbitrary, arbitrary. And now if I show you what sample does, you'll see why you don't do that. Because if the chance is 1 in 2 that some leaf is generated or some branch is generated, and this is tried 3 times, then the expectation value of the likelihood that this stops is 0. That this is expected to not stop is what I mean. So you need to somehow deal with the size. So what you then do is sized n. You need to somehow split it. So this doesn't exist in QuickCheck, but it does in validity, where you need to do gen split 3. So split these into 3 equal pieces so that they sum up to n. Then you resize A, resize B, resize C, and this should do what you want then. We're done.